Welcome. In this video I will be discussing a special category group of compounds known as enolates. Be aware that this is in chapter 19 in the book and we are skipping chapter 19. It contains lots more information than I will cover in this video, but because enols and enolates and related compounds are in fact conjugated, we will cover those in at least the definitions of these kinds of molecules in chapter 20, which is on conjugation. What is an enol? You're already familiar with that. That is a compound that has a double bond with an OH group directly attached. That's called an enol. And if you may remember, enols tend to be unstable. They rearrange to what the so-called keto form, in which the hydrogen from the oxygen moves to the carbon, 3 atoms removed, and the double bond shifts to form a ketone, or in some cases an aldehyde. So this is the so-called keto form. Now be aware, these are not resonance structures. This is an actual chemical reaction in which an enol converts to a keto form. Also, you should know that this is an equilibrium, and that the enol tends to be the less stable of the two forms in most cases. There are a few interesting cases where of the keto and the enol form that you can always draw for any ketone or any enol. In some cases the enol tends to be more stable, but usually it's the keto form that's more stable, and so we'll draw the arrow pointing in the direction of the keto form primarily because it's usually the form that exists under normal conditions. Okay, that's just a little bit of review of enols, but what I want to point out in this particular lecture is that you can take an enol and you can convert it by simply adding a base, pull off the H plus from that oxygen into a negative, what we might recognize as an alkoxide. That is an alkyl group with an oxygen with a negative charge on it. But notice also that there's another resonance structure for this, because now we can move the negative charge down to the carbon. And as we saw in the last video, if a pair of electrons moves down into there, form a double bond, and you move a pair of electrons out onto that carbon then becomes negative instead of the oxygen being negative. And these are, in fact, resonance structures of each other, unlike the keto-enol tautomerism that I showed a minute ago, in which a hydrogen is actually moving. That's the reason those aren't resonance structures, because you're moving an atom. In this case, you're not moving any atoms, you're simply moving a pair of electrons, and that means these are in fact resonance structures of each other. So this kind of molecule is a very important kind of intermediate. It's known as an enolate, meaning a negative enol. And it's given that name because it comes from an enol. But notice, and this is very important, that an enolate could also come from a ketone or aldehyde, in which the hydrogen next to a C double bond O is pulled off using a base, and that would also get you to the enolate. Enolates, therefore, are simply carbon next to a C double bond O in which an H plus has been pulled off to form a negative on that carbon, but it has a resonance structure in which the negative charge is on the oxygen. So whether you approach an enolate from the enol point or from the keto point, it's the same enolate because these are simply resonance structures of each other. Even if you approach it from the keto form, it's still called an enolate. These are very important intermediates, as I said, and you should be ready to recognize when is a molecule an enolate and how could you make an enolate from an enol or from a keto form. In both cases, of course, you're just adding a base. Usually it has to be a fairly strong base because enolates are not particularly good negative charges, although they are resonating with each other and therefore more stable than other kinds of alkoxides. They are, in fact, usually only seen as intermediates and mechanisms, not stable. Most enolates themselves are not stable. Okay, the last point about enolates is that we now have a mechanism, in essence, because these are both equilibrium reactions. Notice that you can go from a keto form to an enol form, or from an enol form to a keto form, and thus we know now how keto-enol tautomerism happens because it goes through an enolate intermediate. There is also an acid-catalyzed mechanism for the formation of an enol from a keto form and vice versa, but we won't worry about the acid-catalyzed format at this point. We'll just worry about the enolate intermediate. Okay, anyway, the point is that the negative charge on carbon, negative charge on oxygen is in resonance with each other, and therefore enolates are conjugated molecules and therefore more stable than other negative oxygens would be. One last type of molecule that we'll talk about in this little video are compounds called enamines. So what do you suppose an enamine is? Well, if an enol is a compound that has a carbon-carbon double bond with an OH group attached, an enamine would have a carbon-carbon double bond with a nitrogen attached, and that nitrogen will have two other things attached to it, whether those two things are hydrogens or carbon groups or some combination of them. But don't forget that amines have a lone pair of electrons on the nitrogen, and therefore this is what's known as an enamine. And that double bond, that lone pair on the nitrogen can conjugate into the system, and you can have another resonance structure in which the carbon takes up a negative charge because it gets a pair of electrons from this double bond. That pair of electrons is moved in there to form a double bond with the carbon, and thus the nitrogen ends up with a positive charge. Again, just as we saw for enols, which have two resonance structures, enamines have two resonance structures as well. And just like we saw with enols, you have a charge separation in the second resonance structure. So of the two resonance structures, this one is by far the more important one. But in enamines, that's actually a relatively important resonance structure. Why? Because notice that the positive charge is on a nitrogen with 4 bonds. We've seen 4 bonded nitrogens before, and they're actually relatively stable, much like the ammonium ion, nitrogen with 4 hydrogens on it, and a positive charge is actually a stable molecule. You can put it in a jar and keep it, along with a chloride or some negative to balance out the positive charge. Well, in this case, these are relatively important because of the stability of the positive charge on nitrogen. But again, just to be clear, of the two resonance structures, this one is more important due to the fact that it doesn't have any charge separation. And that will end this small video. Thank you for your attention.